join us. So last time we were talking about the temperature as one of the parameter of state of the ocean water. And now we will be talking about the salinity. The temperature determines, at its side determines the density, but also salinity determines the density, because the salinity is being, as you can see here, as a total amount of dissolved material in 1 kilogram of seawater. That means that apart from the fresh water, apart the water, we have a dissolved material in the seawater. So which makes the density of the seawater higher than the density of the fresh water. And typically we are talking about 20 per mil or 30 per mil of the density higher than the fresh water, natural water. And here is also the definition of the salinity, which is defined as a total amount of dissolved material in gram in 1 kilogram of seawater, when all the carbonate has been converted to oxide, the bromine and the iodine, replaced by the chlorine, and all organic matter are completely oxidized. So that means, simply saying, that means that the organic matter, so the phytoplankton, zooplankton, they don't enter into the salinity. So the salinity is something neither bacteria. So salinity is something which is all the inorganic material which is contained in the seawater. This definition was indeed difficult to implement in practice, but it was found that the salinity is directly proportional to chlorine in seawater. And since the chlorine can be easily determined chemically, because chlorine can be determined chemically, the salinity was redefined in terms of the chlorinity. So you can see here the salinity you have simply to add a constant and multiply by another constant, you obtain the salinity. Or in an even more simpler way is this one here. So that's the first definition of salinity, and the first practical way of obtaining the salinity when there were no available other methods. So we were determining the salinity using the chemical analysis. Later on, there is even better and faster and more practical measurements of salinity, which is based on conductivity. Because, since we are talking about the dissolved material, that means that the salt water, the seawater takes the electric signal passes through it. So the salinity based on conductivity, and a practical salinity scale of 78. In 1978, there was a first definition of the practical salinity based exclusively on the relationship between the conductivity and salinity. So the various definitions of salinity works very well because the ratio of various ions in seawater are constant independently on salinity. This is another important characteristic of which is essentially what the formula here says, that the various ions are constant independently on salinity. So independently how high is the salinity, this is a constant 1.805. The relationship between conductivity and salinity has an accuracy of around 0.003 in salinity. So, you remember yesterday, the day before yesterday, we were talking with the accuracy of temperature, which is on the order of 10 to the minus 3, which is the same thing, more or less the same thing. We have the accuracy of the salinity. And this is something what we need in order to describe in a satisfactory way the water masses, because the variations in salinity, temperature, and in the open ocean are such that the accuracy of 10 to the minus 3 is good enough to distinguish between different water masses. Because water masses, you will see later, water masses are defined by their salinity and temperature. Now, obviously, we have now the density. The density is obtained using the temperature and salinity. And absolute density can only be measured in special laboratories with an accuracy of 4 parts per million. In oceanography, we work with density relative to density of pure water. So the pure water has a density 1 over 1,000 kilogram per meter cubic, or 1 gram per centimeter cubic. And so we are working with the density relative to density of pure water. As I said before, due to the dissolved material, the density of seawater is higher than the density of pure water. In practice, the seawater density is calculated from in situ measurements of pressure, temperature, and salinity. These are from this we have an equation of state of seawater using these 3 parameters. Seawater density is typically, as you can see here, is 1 in 1,027 kilogram per meter cubic, which is this is a typical density in the open ocean. In the for example, you will see later that in the Mediterranean the density is 1/29 or 1/28. So we are talking about the 26.7 to 29. 27 to 29 kilogram per meter cubic, and we in oceanography we are using only the last 2 digits, which is the density anomaly, because we don't need to take all these 1,027,000 is always there. So we do the difference. We define the density anomaly as a real density minus 1,000. Potential density is obtained from the equation of state using the potential temperature, since the pressure influences primarily the temperature. And if you remember here, let me see. No, it's not here. Let's try to. Here it is. You see, that's the temperature in situ temperature. So that means that the temperature what you measure at a certain depth at a certain pressure, and this is the potential temperature. As you remember, I told you the day before yesterday, by using the in situ temperature, we obtained at a larger depth, we obtained the instability. Instability, why? Because the deeper layer density is lower than the lower layer densities. So, and this is not possible in the ocean because it mixes very, very quickly. Therefore, we introduced the potential temperature, and using the potential temperature, we calculate the potential density. And so you can see that the potential density curve straightens and becomes vertical. And so we eliminate this instability, apparent instability due to the usage of the potential temperature. Where are we now? Okay, density. So potential density is not useful for comparison of water masses at greater depth of several kilometers, since the relationship between temperature, salinity, and density is not linear. As a result, 2 water samples having the same density but different temperature. And salinity at a depth of 4 kilometers have noticeable different potential density. So we have, in order to compare samples from great depth, it is better to bring both samples to a nearby depth instead of the surface. For example, we can bring both parcels to a pressure of 4,000 decibars, which is near a depth of 4 kilometers. So we can also use another type of potential density, where again, essentially, we do the same thing. We bring the parcel at a certain depth to the depth we decide as a relevant depth adiabatically, and so that's how we eliminate the instability. Here, where we are talking about these great depth, we are talking about the larger than 4,000 or 5,000 meters. And since and these are very limited parts of the world ocean. Okay, so now let's see. Let's see the salinity. Salinity. What depends salinity on? The salinity depends on the amount of water you add to the ocean, and on the water the ocean loses. So how do we add the fresh water to the ocean? We add by rivers, river runoff, and by rainfall. We subtract the fresh water from the ocean. We subtract it by evaporation. So by adding the fresh water, obviously the salinity decreases. By subtracting the fresh water, the salinity increases. So typically we talk about the sea surface salinity, or salinity in general, in terms of the evaporation minus precipitation. Obviously, what is happening, the sea surface salinity is the salinity which depends on these differences, evaporation minus precipitation, because both evaporation and precipitation are processes acting on the ocean surface. So you may ask yourself, and how these salinity signal, this salinity changes in space and time, how they propagate vertically, since major changes of the salinity appears in the surface layer. It happens, or it takes place, thanks to the vertical mixing, to the processes which are they are redistributing the water masses in the vertical and also obviously in the horizontal. You may see here that here we don't have so we should have evaporation minus precipitation and minus rainfall. This is the exact parameter which determines the salinity. But rainfall, precipitation. So in precipitation we have a rainfall and river runoff. River runoff is influences of the rivers is mainly limited to the coastal area, because the river water is expanding or redistributing over the limited area along the coast. It doesn't, river water doesn't go far into the center of the ocean. And in fact, here is an interesting graph which shows how the evaporation minus precipitation determines the salinity over the world ocean. So this is the minus 90 is southern pole, and plus 90 is northern pole, and continuous line is the evaporation minus precipitation, and dashed line is salinity. And what you can see is that these two curves follows each other very, very well. There is a minimum evaporation minus precipitation in near the equators, where the precipitation is larger than evaporation. Then you have here in the mid latitudes around the 30, in subtropical areas around 30 degrees north and 30 degrees south, you have a higher and the evaporation is larger than precipitation. Then again, in the mid latitudes around 60 degrees, the precipitation is larger than evaporation. This really reflects what is happening in the Earth climate. Here is the precipitation is large around the tropics. Then you have the strong evaporation in subtropics, and you have relatively strong precipitation in mid-latitudes when you have the passage of the cyclones, which are bringing the fresh air from the ocean, and where is a strong vertical convection and strong action of cyclones, mid-latitude cyclones. So this is how and salinity. You can see the salinity really follows pretty well what is happening in the climate, in the ocean, in the atmosphere. Evaporation minus precipitation in millimeter per day, and here is the 40-year average. And here you can see that mainly in the first approximation, the distribution of evaporation minus precipitation is such that it's negative in a belt near the equator, but there are also areas where it's deviates from this area. Then you have in subtropical areas, you have a belt of E minus P positive, so evaporation larger than precipitation. And then finally, in mid latitudes, you have evaporation minus precipitation, again negative, as it is in equatorial areas. The previous diagram, this one is simply done that we did the zonal average for each belt from -90 to +90 over the entire world ocean. How about the vertical distribution of? We said before that both temperature and salinity are determined by the processes which are taking place at the surface. Therefore, one may ask ourselves, and how come the signal, so that would mean that the signal is maintained at the surface, but that's not true. The signal, which is, or the variations of the temperature and salinity in the surface, are felt over the entire water column, or over the most part of the water column, directly or indirectly, through vertical mixing and horizontal transport in deeper part of the ocean. Here is how the vertical distribution of temperature looks like. Here is the scale. You can see the temperature goes from 18 to 30. This is a station, Bermuda Atlantic Time Series station, which is in the Atlantic, and you can see for different seasons or for different parts of the year, how the vertical distribution of temperature looks like. Let's look at into more details. For example, in August, what's happening in August? In August, we have a maximum temperature in the surface. Here is in this specific place, we have about 29 degrees in a very thin surface layer. So it goes quickly down, and after 150 meters reaches the minimum, which is around 18, 19 degrees. So you have the drop of the temperature of the seawater temperature from 29 to 19, so 10 degrees in 200 meters. This is August, so that means this is summer. So there is a major insulation in the surface layer. So the ocean gains more heat than it loses by long wave radiations. Because insulation is larger than all the terms of the heat laws, if you remember the heat budget equation. When we go to September, September is slightly different. September, you have the vertically mixed or the practically constant temperature from surface to 50 meters, and it is around 24, 25 degrees, almost 26 degrees. And then there is a sudden drop of this temperature with depth, and then finally reaching more or less the same value as it used to be in August. This layer here, which is here from about 50 meters to about 100 meters, where you have a strong gradient, vertical gradient of temperature, strong changes of temperature with depth, this is called the thermocline. Thermocline is the layer of the maximum vertical gradient of temperature. And then you got this almost constant temperature with depth if you go below 150 meters. Why is this surface layer with the almost constant temperature here? Because even passing from August to September, there is more events of the wind. So wind, what causes wind? Wind causes the vertical mixing. So vertical mixing means that the water from this very surface is mixed with deeper layers. So if you do the integral over here and compare with this thing here, you will get the same surface. So the amount of heat which is contained in this part of the water column is redistributed over the larger water column, and therefore the temperature is lower, but is vertically mixed. So this vertical mixing is due to the wind events. When you go to November, November is when the influence is even stronger, and therefore you have a practically very well mixed surface layer from 0 to almost from 0 to 80 meters, and with constant temperature. Again, you have a thermocline, and then the deeper layer, the temperature doesn't change too much. In this deeper layer, the temperature doesn't change too much because it doesn't depend on whatever is happening in the surface. In deeper layers, the possible changes of temperature can be due only to horizontal advection. Rather not so often the temperature, the surface processes are influencing the deeper layer. We will see later that there are some specific places in the world ocean when the surface processes are can act or can determine the variations of temperature. And so forth. You can see that in January the curve is even more vertical. In April is the same. So by having these influences of the wind and also the surface cooling, what is happening is that the curves, the vertical distribution of temperature, or the curve of the vertical distribution of temperature becomes more and more vertical, or in other words, temperature becomes more and more constant with depth. This is, as I told you before, this is due first to the wind influence. But second, can be another very important process is that if you cool the surface, what is happening? The surface temperature becomes smaller, lower and lower, and the density, which depends on on temperature, density becomes higher and higher, because lower temperature means higher density. And so that means that in the surface there are situations where for a very short period of time, the sea surface density is higher than in deeper layers. This creates the instability and the vertical mixing. Okay, so and this vertical mixing then again helps to make this curve vertically mixed. So there is on one hand there is a wind, so mechanical forcing, and on the other hand there is this thermal force or the cooling of the sea surface layer. We will be talking about this later, because this is the cooling of the sea surface layer is one of the essential processes which determine the world ocean circulation. Here is the for your information, for your idea, this is sea surface temperature climatology for January. And you can see that there is this belt around the equator with a relatively high temperature, sea surface temperature, which goes up to 30, 32 degrees, over 30 degrees. And then obviously in polar areas, the water is relatively cold. It goes up to -2 degrees Celsius. So you have this temperature range between the equator and polar areas around 30 degrees. So it's a huge temperature gradient between the equator and polar areas. The same thing for July, more or less, is the sea. You see there are slight changes simply because of the differences between northern and southern hemisphere and the northern and southern winter. But essentially the pattern is this one, okay? And here is the sea surface temperature anomaly, for example. These data are obtained from satellite. And you can look and calculate and see the climatology of these data. Comparing the different years with their long-term average and so forth. So this is one example how we do that. Then we have something, another important, interesting parameter is interesting statistical description of the sea surface temperature is the annual range of the sea surface temperature. Annual range of the sea surface temperature means that the difference in temperature between the winter and summer, maximum and minimum temperature. And what you can see here is that the annual range of the sea surface temperature is smallest in the zone of the equator, where you have the small differences between the summer and winter. On the other hand, in mid-latitude, there's a rather strong range between the summer and winter. And also there are these tongue of the strong range of a temperature on both on the western side of both Pacific and the Atlantic, which we will see later. This is due to the Gulf Stream of Kuroshio, the most important world ocean current system. What about sea surface salinity? Sea surface salinity is obtained from the measurements, and you can see that here is another interesting pattern. You have a relatively high salinity in subtropical areas here and there, and these subtropical areas are the high salinity values correspond to the E-P positive values. What that means? That means that evaporation is larger than precipitation. So that means that the losses of fresh water is higher than precipitation. But this is not valid only for the ocean. In the ocean, you can see this signal very easily from the salinity. And on the land, you can see that these E minus P positive and or reddish areas in the salinity corresponds to the presence of the deserts on the land, on the continents. This is the African desert. This is the desert in the United States, and here is the desertic areas in the Asian continent. Also, the same thing is in Southern America. So you have the E minus P is a parameter which determines characteristics not only in the ocean but also in the atmosphere. Sorry, on the continents. How about to get you an idea how is the mean temperature of the ocean? So the mean temperature of the ocean is 3.5 degrees Celsius, because it's something which is, for me, it's very, very surprising. And because so far we were showing the temperature of 30 degrees on 25, major part of the ocean has a 25 to 30 degrees temperature, sea surface talking about sea surface temperature. But if you do the average over the entire volume, then you get a temperature of 3.5 degrees Celsius. That means that the major part of the ocean, or the volume of the ocean, has the very low temperature. And indeed, in fact, the temperature of the deeper layers is around 5 degrees Celsius or even less. And so that and the major volume of the ocean is contained in the average depth of the ocean is 5,000 meters. The mean salinity is 34.7 kilogram per meter cubic. The distribution about the mean is small. 50% of the water is in the range 1.3 to 3.8 degrees. So major part of the volume of the ocean has the temperature between 1.3 and 3.8. You can see now why we do need these this high accuracy in measuring the temperature. The same thing is valid for salinity. Salinity range is only 0.2 kilogram per meter cubic, so 34.6 to 34.8. So this is another illustration. How do we and why do we need this high accuracy for measuring both temperature and salinity? But let's skip over this because okay, I'll skip over this one here. Just to give you an idea how the vertical distribution of temperature looks like in, for example, in the Adriatic, and temperature and salinity looks like in the Adriatic, where we will learn by looking at this specific situation. We will learn what are the processes which are determining the vertical distribution of salinity and temperature in a sea, in an ocean, or in a sea. Here is, for example, the vertical distribution of temperature in this area, in this transect here. This is you start from the coast and go toward the open sea. This is the coast here, and the open sea is here. Here you have depths only up to 50 meters. And if you look at the different seasons, this is that's a spring season. In a spring season, the temperature first of all goes from 15 to 10 to 12 degrees Celsius. This is the Adriatic, and we are talking about the 50 degrees depth. So we are far away from the area, from the world ocean, where the mean temperature is 3.5 degrees. But here the temperature is obviously something around 12, 13 degrees Celsius. And you can see, take into consideration this is a distance in kilometers. So we exaggerate the vertical scale with respect to the horizontal scale. And what you can see is In the surface layer, there is a slight vertical gradient of temperature. We are talking about the springtime. In springtime, the heating starts. So you have a slightly warmer surface layer with respect to the bottom layer. When you go to summer, you can see that the heating was felt at 10 meter, up to a 10-meter depth. So you have a 24, 25 degrees Celsius up to 10-meter depth, 10 to 15, and below then you have the strong vertical gradient of temperature, and then finally in the bottom layer, more or less the temperature remains the same as in spring. So the heating is taking place up to 20 meters, and then below you have the temperature, which essentially doesn't change too much. If you go to autumn, what is happening? It's happening that the vertical mixing or the wind influence pushes this gradient, vertical, the thermocline. This is the thermocline where the isotherms are close to each other, pushes it down. Here is the thermocline is at around 20 meters. Here is already at around 40 meters. You know, it was pushed by the wind mixing, and then essentially below the thermocline, the water column, the water temperature becomes constant, doesn't change. Going to winter, the vertical mixing, what causes the vertical? The vertical mixing or the wind or the cooling practically makes that the water temperature is constant from the surface to the bottom. And so you have only the horizontal, or you have practically the horizontal gradients of temperature. The vertical gradients of temperature are very weak. In addition, the temperature over the entire area is around 12 degrees, as it was in the bottom in other seasons. Okay? What about salinity? Salinity should show another pattern, should show another processes, because the temperature shows the heating, surface heating and cooling, while the salinity should show evaporation minus precipitation and river runoff influence. Therefore, when we hit essentially the high temperature, that means that there is no influence of fresh water. When we, on the other hand, when we see someplace the patches of the fresh water, that would mean that, or lower salinity, that would mean that there is an influence of the fresh water. So let's look at the salinity in spring. You remember temperature is this is a pattern of temperature, and salinity, what shows the salinity? The salinity shows relatively high salinity at the open sea. Okay, see, it's salinity here is 38 kilogram per meter cubic, more or less. But here is an essential pattern, essential feature. You can see that near the coast, this is around 20 kilometers near the coast, there is this patch of the relatively fresh water, of low salinity water. One should ask how this comes from. So that means that there should be some freshwater source. It's certainly not the rainfall, because rainfall would be felt over the entire water, or the entire surface. So it should be the river runoff, because it is, as I told you before, it is limited to the very thin coastal area, the coastal area of around 20 kilometers. And in fact, here, in this specific place here, south of Venice, there is a large river which enters into the sea. Its flow, or its fresh water coming from that river, expands along the coast and flows southward. as I told you before, this fresh water coming from the river doesn't expand over the larger part, but is kept along the coast. And indeed, in a belt of around 20 kilometers, you can see that there is this patch of the fresh water. Take into consideration water having the lower salinity is also at the same time is kept at the sea surface layer, and therefore the strongest low salinity water is in the surface layer. So that's the situation how it is in a spring. So we have a relatively strong freshwater river discharge because there is a lot of rain in this specific season, and the salinity is minimum, and you have this patch. However, this low salinity water is maintained also in a summer, and you still see these around 10 to 20 kilometer fresh water, but this fresh water then spreads also in the surface layer over the larger part of the sea, and the higher salinity remains below. So you have here in a certain part we have the higher vertical density, vertical salinity gradient, strong vertical salinity gradient, and this is what we call hallock line, the high vertical salinity layer, hallock line. If you go to autumn is again the signal is maintained there. If you need these terms, you just write me a mail, and I will send you the terminology, so you can remember that. When we used to have the lectures in physical in presence, then I would be writing, but now I can write. Anyhow, this is in autumn again. This low salinity layer remains in a coastal area, but this is larger than, you can see it's larger than in spring, because there is more fresh water coming in autumn. There is more rainfall in autumn, and therefore there's more freshwater discharge by the river. The rest is more or less remains unchanged, and the salinity at the open sea is around 38 degrees, 38 kilogram per meter cubic. If you go to winter, then the whole open sea area becomes vertically mixed. Everything is mixed because of the mixing which appears due to the wind influence, to mechanical mixing, and due to the losage of heat in the surface layer. But still, in all these seasons, the signal associated with the river runoff remains. So this is how this process acts on the vertical distribution of temperature and horizontal distribution of temperature and salinity, and how you can recognize. I don't go into details for other transects, which essentially shows the same thing. And let's see, yeah, okay. So these are all these transects which I want to be talking about this too much. Now, maybe we'll be coming back to these to some of these graphs while discussing the other processes. Mainly the processes of the vertical of the formation of the dense water or the vertical convection. Now we'll be addressing the motion in the ocean, motion in the ocean is dynamics. The basic equations of fluid motion are based on the conservation laws, and we have a number of conservation laws, like a conservation mass, which leads to the continuity equation. So the mass, the ocean mass, is not lost or gained. And we have a conservation of energy, conservation of heat leads to heat budget. We have a conservation of the mechanical energy, which leads to the wave equation. We have conservation of momentum, which leads to momentum or Navier-Stokes equation. And finally, we have conservation of angular momentum, which leads to the conservation of vorticity. So these are the five conservation laws, which gives us the five different equations which are be used to solve the problem in geophysical fluid dynamics. The dynamics is determined obviously by the forces. So we have on one hand we have dominant forces. On the other hand, we have other forces. Dominant forces mean these are the forces which are responsible for large scale circulation, which are present all the time, and which determines the motion in the ocean. Then we have other forces which are of the minor influence, and they are less important than the first three forces. We have a gravity force, which gives rise to pressure gradient, buoyancy, and tides. We have Coriolis force, which is the apparent force, which results from the fact that the motion is on a rotating coordinate system. And finally, we have a friction, which is due to a relative motion between two fluid parcels or between two fluid levels. One of the important frictional forces is the wind stress. The wind stress is the frictional force between the atmosphere and the ocean, but relative motion between the two fluid parcels exists also in the ocean itself, because there is always relative motion between different parcels in the ocean, or there is a relative motion between the ocean and between the water masses and the bottom. Also there we have a frictional force. Other forces are atmospheric force, which results in inverted barometer effect. We call it the inverted barometer effect, which means that for 1 decibar of increase of the sea level, we have 1 centimeter of 1 decibar of increase of atmospheric pressure, we have 1 centimeter of decrease of sea level. The higher is the atmospheric pressure, the lower is the sea level. If you go now, for example, I think we are in a period of relatively high atmospheric pressure. You will see that the sea level, if you go for a walk along the shore, you will see that the sea level is relatively low. It's low because the atmospheric pressure is relatively high. Then we have a seismic forces. Seismic forces are acting very violently, but they are limited, very limited in time. They don't really act violently, but they have very dramatic results. They result in tsunamis, which are driven by earthquakes. And so tsunamis is simply obtained, is due to the resonance between the waves which have been formed in the open ocean, and then while reaching the coast, they enter into the resonance and becomes very high sea level oscillations. Some of you have heard for a number of tsunamis. The very dramatic one was in 2005. If I do remember well, when there was this in Indian Ocean tsunami, which it was 24 December 2005. I was in India at that time, and so that's why I remember that. Okay, so and you can see I survived. Okay, so let's see what kind of circulation do we have, because the circulation is on one hand defined by its dynamics, and on the other hand, and automatically follows from that, is defined on the time and space scale. We have as a first basin-wide circulation is the general circulation of the world ocean, which is the permanent time average circulation. How do we get this? How do we get this general circulation? General circulation we obtained is as the same definition says, is time average circulation. So if you do the measurements at a certain point in the ocean, how you would get the general circulation component? You simply get the general circulation component by doing the measurement at a single point and for the for the period of time enough long in order to get the permanent circulation. So it's not the longer your measurements are, the closer is the current you measure to the general circulation component. Then we have abyssal circulation, or also called deep circulation, which is the circulation mass in the meridional plane in the deep ocean, driven by mixing. As I told you before, general circulation, if we are talking about the surface, general circulation in the surface is determined or generated by the differences in temperature and salinity, which are determined by differences in the evaporation minus precipitation and differential solar heating between different parts of the different latitudes. Abyssal circulation, on the other hand, is determined again by the differences in temperature and salinity. But in that case, the difference in temperature and salinity is determined by the vertical mixing and not by the direct influence of the solar heating, for example, or evaporation minus precipitation. The influence of the solar heating or evaporation minus precipitation has been transferred to deeper layers by the vertical mixing. So this is why it says driven by mixing. We have a wind-driven circulation, which is as you can imagine, as limited to the upper kilometer of the ocean, and is forced by the wind, and can be caused by local wind or by winds in other regions. So can be caused by the wind, which acts at the place where you stay, or as the consequence of the wind blows in some other region, and you get the signal from other region. Gyres are wind-driven cyclonic or anticyclonic currents with dimensions nearly that of ocean basin. So you have a huge cyclone, right? Anticyclone, huge clockwise or anti-clockwise circulation on inward oceans, which are wind-driven and exist over the world ocean, and they have the dimension large as the ocean. So you have they have a diameter on the order of 10,000 kilometers. So it's a huge circulation system which exists there. We have boundary currents or currents flowing parallel to the coast. And these boundary currents are, you will see later that they are determined by these differences in heat content or temperature between equatorial and polar areas. So we have a western boundary current, which is on the western edge of the ocean, which tend to be fast and very narrow jet, such as Gulf Stream or Kuroshio. So they are limited. We'll see later how do we explain that they are very narrow and very swift on the western coast, and then we have eastern boundary currents which are weak and going in the opposite direction. So like a California current which goes southward, you have in the Atlantic also the current, North Atlantic, you have the relatively weak and slow and large eastern boundary current which flows southward. So it's a kind of, and this, if you can see that this, they make part of this anticyclonic or clockwise gyre. Along the western coast, you have the western boundary current which flows northeastward, and along the eastern coast of the ocean, you have the large and slow current flowing southward. So this is already a huge, they make part of the huge anticyclonic or clockwise gyre. You will see that this can be or wind driven, but also can be driven by the differences in temperature and salinity. Both forces, frictional force, so wind and gradient force, and differences in temperature and salinity, mainly in temperature, are determining the same pattern of the current. Then we have skirts or jets, are long narrow currents with dimension of a few hundred kilometers that are nearly perpendicular to west coast. These are relatively small scale structures, few hundred kilometers, with respect to clockwise or anticyclonic gyre. Yeah, they are relatively small. And finally, we have the mesoscale. These are turbulent or spinning flows on scales of a few hundred kilometers. Consider that few hundred kilometers is the scale of these mesoscale eddies in the ocean, but they depend on how, in general, how big is the sea we are talking about. If we are talking about the Mediterranean, for example, or the ocean, or the sea, which is on the order of the Mediterranean or other smaller scale seas, obviously in that case mesoscale eddies are of a few tenths of kilometers, not few or hundred kilometers, few tenths of kilometers. So it can go from few tenths of kilometers up to a few hundred of kilometers in function whether we are studying the ocean or we are studying the smaller sea. Now we have something which is called the thermohaline circulation. So there is no wind here. We can have this kind of circulation where there is no wind at all. So the circulation, north-south circulation, or as I told you before, the large circulation over the world ocean can exist also without the wind influence. And this is thermohaline circulation, so influenced by temperature and salinity. So it's why it's called thermo is temperature, haline is salinity, thermohaline circulation. What is going on here? Here you can have if this is the equatorial region, you can have the heating which is stronger than the cooling in the equatorial area, and then you have a cooling which is stronger than heating in the polar areas. So here you have a continuous pumping of heat into the surface layer, while here you have a continuous loss of heat. As a result of this thing here, the cooling in the polar areas, what is happening? Cooling in the coastal area means that in the surface layer, the seawater becomes colder and colder. By becoming colder and colder, its density increases. By having this increased density increase, the there is the surface water becomes heavier than deeper water, and therefore the surface layer water sinks down. So you have in the polar areas, simply due to the heating and cooling, differential heating of the water, you have the vertical sinking of the surface water. This water then spreads in deeper layers southward, and due to the continuity, because no water can be lost, due to continuity, there is the recall of the water from the south toward the polar areas. So after sometimes you get this steady type of circulation, which is this thing here. You have a vertical sinking here in the polar areas. You have the upwelling, the upward motion in the equatorial region, and then you have a poleward flow in the surface, in the thin surface layer. You can see here that there is also the thermocline, which has this kind of slope. Okay, and here, obviously, in polar regions, there is no thermocline, because thermocline is destroyed by this vertical sinking. Here, in the rest of the ocean, thermoclines exist all the time because it separates the surface warmer layer from the deeper layers. In the polar regions, there is no thermocline because there is a vertical sinking which destroys the thermocline. And finally, we get something which is called global conveyor belt. Global conveyor belt is the global world ocean circulation, which is schematized in this simple way. And how it here, this is the key area for driving the global conveyor belt. In the surface layer, you have here the vertical mixing. You can see the bluish belt is the deep circulation, while the yellow or orange belt is the surface circulation. So what you get here in the Atlantic, this is Atlantic, you get here this vertical sinking. This vertical sinking doesn't exist in the Pacific, because in the Pacific doesn't go to the north enough that the heat loss is larger enough than heat gain in order to create the vertical mixing. Then you have the spreading of this cold water going from the Atlantic and going to the Pacific, and doing its tour around the entire world ocean, and then slightly and slowly it wells up, and then comes back into the surface layer, and then is going back into the area where there is a dense water formation. And here we are missing some parts where there is also dense water formation, which is here around the Antarctic. And then there is this outflow of the Mediterranean, where the dense water comes from the Mediterranean. The dense water from the Mediterranean comes because the Mediterranean has a higher salinity than the Atlantic. Salinity in the Mediterranean is typically 37, 38, while in the Atlantic is 35, as we have seen before from the average salinity of the world ocean. So this is the schematic world ocean circulation. If you put the particle here and just for a scheme, and to give you an idea how slow is this motion. If you put a particle here in the Atlantic, sorry, where is why don't I see the here it is. if you put the particle here, it would take for this particle to go to do all these this path and comes back around 1,000 years. So the residence time, we call it residence time, of a particle is around 1,000 years. 1,000 years is the time needed to refresh this water, which starts its path from for example, from the place where it is lost. So heat loss in polar areas is the engine that drives the global conveyor belt. And this global conveyor belt here is based purely on the considerations of the heat loss of the world ocean. One part of this circulation of this global conveyor belt is this Gulf Stream. You can see this Gulf Stream which goes northward, in a certain point leaves the North America coast and goes toward Europe, and then comes back here, and here you have a sinking. And in fact, this is how it looks, how the Gulf Stream looks like from the satellite. This is the sea surface temperature image from the satellite in a specific. This is a snapshot of the Atlantic Ocean. If you recognize, this is the coast of America. Here, that's Florida, and this is the ocean. The more red is the color, the warmer is the sea surface, or the more blue, or even this thing here is very cold and very cold area. So what it happens that this is Florida. This current, this warm current this is Cuba. This current was generated and has origin in the Gulf of Mexico, and then goes northward as a part of this thermohaline circulation, goes northward, and then at a certain point leaves the American coast, and then crosses the ocean and goes toward the European continent. At the same time, you can see this is a very huge area of very cold water. But the Gulf Stream is not simply a river. It's wide, like 100-kilometer wide. It's very swift. The velocity goes up to a meter and a half per second. But it has a number of anomalies in it, if I may say, anomalies, and these are the mesoscale eddies or mesoscale eddies which are formed here, which you can see. These are they are detached from the Gulf Stream and takes this cold water from the coastal area toward the open sea. So the Gulf Stream is not a simply straight flow of water, but it has the meanders, has the eddies, and which are changing, which are on the order of a few hundred kilometers, and they live for about 3 months to 6 months lifetime. And here is the scheme of this circulation. You can see that there is a cold water is coming back on the left hand side of the Gulf Stream, and this is the Gulf Stream, and these are the cold water eddies, and here is the warm water close mesoscale structures on the left hand side of the Gulf Stream. And here is how these eddies are formed. You can see that at the beginning the Gulf Stream, or even the other very swift current, has only a meander. This shape is called meander. This meander becomes larger and larger, and then the instability was formed, and finally the eddy is closed and is detached from the Gulf Stream, from the mainstream. This is the scale, and you can see that these scales is in kilometers. So we are talking about the 100-kilometer scale here. Here is on the order of 100 kilometer. Here is we zoom this. We zoom our global conveyor belt only to this area of the North Atlantic, and this is the North Atlantic current, which is really the current which is coming from the Gulf Stream and becomes Norwegian current, and then you can see that brings the relatively warm water to both England and Norwegian. So that's why Norwegia or England are warmer than the Canada coast, because we have a relatively warmer water flowing northward with respect to the cold water which goes southward along the Labrador Sea, along the Canada coast. So this is how it looks like if you zoom. In Labrador Sea, there is a dense water formation. There is a strong cooling, which then creates this southward deep water flow. How this process looks like? This process of the dense water formation. Since this dense water formation is a driving engine of the world ocean circulation, we should know how, and it was studied to a large extent by oceanographers in order to understand how it looks like and how it is evolved, and what is the driving forces of this. What are the typical scales, temporal and spatial scales of this process? And here is how it looks like. What are the phases of this dense water formation or the vertical mixing? We have a preconditioning. What is the preconditioning? Preconditioning means that the sea has prepared itself to the vertical mixing, to the dense water formation. And preconditioning means that there is this kind of shape of the isopycna. These are isopycna, so the lines of equal density. And you can see that there is the formation of the high density in a certain area. So this certain area shows the formation of the high density, and there's a relatively limited area, and which, if you look from up, you can see that how it looks like. So you can, this is this dense area, but here you already here you don't have a strong losses of heat. When the strong losses of heat start, you can see that there is the vertical mixing below. This is the cross section. Can you follow this? This is, you can see the cross section, and the vertical mixing takes place, and then you have these the sinking of this water from the surface, which becomes heavier and heavier. And then there is and outside of this is a strong horizontal gradient of density, and then outside of that area there is no dense water formation at all. So the dense water is typically formed in a very limited areas, and due to the specific preconditioning of the sea, and which then ends up in the formation of the dense water. So, but these processes which are taking place there are responsible for the formation of the huge volume of the water, because this has to drive the entire global conveyor belt. Okay, and here is how it's the final shape of this thing. Here is that everything is vertically mixed up to a certain depth, and you have here along the border of this patch, we call this cold water patch, there is these meanders, which then finally destroy this patch once there is no strong surface heat losses. And here is how this patches look like. And here's the concrete. There is the real example of the Labrador Sea, where you have here the circulation. The surface circulation is this way here, and here you have this huge patch, which huge preconditioning patch, which is then where you can have the wind which blows from the cold continent here, from the Greenland, brings the cold air over the sea, cold and dry air. This cold and dry air, what it creates? It creates, on one hand, the cooling, and on the other hand, it generates the increase of salinity. So both cooling, lowering the temperature, and increasing of salinity due to the higher evaporation and precipitation, due to the influence of the continental dry wind. Both of these processes are increasing the density of the surface water, which then creates this strong, vigorous vertical mixing. Okay, let me see. Let's see how it looks like. In the Adriatic, we have the same process. We have the formation of the dense water due to the cooling of the surface layer, and the cooling. So that means that we have the wind which blows from the coast toward the open sea, which is dry continental air, and which then is cold and dry continental air, which then, as I told you before, causes the surface water cooling and the stronger evaporation. How it looks like if you do the measurements, if you do the temperature salinity measurements in the area right after the vertical mixing, what would be the pattern of the potential temperature? This is the cross section of the potential temperature across this patch. You remember this page, what we were talking about? In the surface layer, this is already the vertical restratification takes part. But what you can see is that there's a huge area from, sorry, this is not really the Adriatic, but this is really the Labrador Sea, but that's the same thing. Anyhow, what you see is that these are the data from July 1990. So July means that you already have the cold season, because the winter season is behind you, but the signal of this pass vertical mixing stays there, because this huge area from 500 to 2,500 meters of the vertically mixed water column, potential temperature is practically constant, is all the time in 3 degrees. Salinity is also vertically mixed, and the density. So that means that the vertical mixing reached 2,500 meter depth. So all the water column from zero, from the surface to the bottom to the 2,500 meter is vertically mixed, where this dense water is formed, which then enters into the global conveyor belt and drives this global conveyor belt. Here is the numerical simulation of the mixed patch, just to show you that it's relatively easy produce it in a numerical model, and how it evolves with time. There is another, how do we, let me show you a signal of this, of sea surface signal of this vertical mixing. As I started to talk to you, the Adriatic is also the place of the dense water formation. Here is the Adriatic, southern Adriatic part where the dense water formation takes place. Here is piece of Italy. That's Italy here. Here is Albania. and here is the Croatia. And what you can see here, his Albania is here. What you can see here, these are the satellite image of the chlorophyll distribution, sea surface chlorophyll distribution obtained from satellite. Why are we looking at the chlorophyll distribution while studying the dense water formation? Because the signal which comes from the dense water formation can be seen from the chlorophyll. What is the chlorophyll? The chlorophyll is the chlorophyll concentration is the sign of the concentration of phytoplankton in the sea. Phytoplankton are ocean plants. Ocean plants, as the land plants, they have chlorophyll. So the more chlorophyll is present in the sea, the higher is the biomass of the phytoplankton. Phytoplankton is fed on, consuming the nutrients. Nutrients are used for phytoplankton to grow. Nutrients usually they stay in the deeper layers, in a layer below 150 meters. So there should be some process which bring these nutrients into the surface in order to generate the phytoplankton bloom, the growth of the phytoplankton. And if we have the vertical mixing associated to the dense water formation, that means that we are mixing the water from deeper layers to the surface. In other words, we are bringing the nutrients into the surface layer. Apart from that, there is another important role of the vertical of the dense water formation is that the water which stays at the surface is rich in oxygen. If we have this vertical mixing from the surface to deeper layers, that means that this vertical mixing on one hand brings the nutrients into the surface layer, but on the other hand it brings the oxygen to the deeper layers. So it's this kind of processes. So the dense water formation processes are ventilating the deeper layer. They act as windows for the ocean. As you know, you open the window. Why? To ventilate your room, because if you have many people in one room, you have to open the window in order to ventilate it, in order to avoid the concentration of CO2, for example. The same thing is happening in the ocean. If we don't have these dense water formation sites, the ocean would not be ventilated, so there will be no oxygen in deeper layers. There will be no life in the deeper layers. So this is another side effect, but extremely important effect of the dense water formation. Anyhow, here in this specific case, we are looking at the signal associated with the dense water formation, which appears in a horizontal distribution of the phytoplankton. So let's look at this series of images, which are, one is March 16, then we have March 19, then we have April 4 and April 15. So we have like every 5 to 10 days satellite images. So and they are very different from each other. Let's see the first one. The first one what shows. First of all, let me explain to you a color scale. Brownish color or reddish color are the high concentration of chlorophyll or sediments in general. Bluish color means that there is a very weak, very low concentration of phytoplankton. So what we see here is, first of all, let's forget about these coastal areas. In coastal areas, you have a lot of sediments. It's not necessarily the phytoplankton. And these coastal areas are rich in nutrients because you have a river runoff, so there is a lot of phytoplankton, but also sediments. In the open sea, on the other hand, the phytoplankton concentration or the chlorophyll concentration depends only on the availability of nutrients which are brought to the surface by the vertical mixing. Therefore, at the beginning of this process, or this is March 5, which is the winter, we can see that there is a low chlorophyll concentration in the center, in this patch in the center of the Adriatic, because there is a low concentration of phytoplankton. There is not enough nutrients, but you can see also that there is a number of that this patch is not very, it's very undulated, and you have these number of meanders there. Once when you look at the next image, it looks like negative of the previous one. You see that the center, that this patch, which exactly corresponds as a form to this bluish one, this is reddish one, they correspond to each other as a form, but here the concentration is much more higher than it is here. So here, obviously, we pick up the process when after the vertical mixing. Here, there was no vertical mixing. In the meantime, between this and that, what happened? It happened, obviously, some strong wind event with caused the vertical mixing due to the cooling and due to the evaporation, and brought the nutrients into the surface layer. There was a strong bloom of phytoplankton, which then exactly described this patch of the vertical mixing area. And very soon, and after less than 10 days, the concentration of chlorophyll diminishes strongly, because the phytoplankton, what it did, it has a lifetime on the order of 5 to 10 days. They grow very quickly. They consume all the nutrients and start to decline. And so you have here the declining of the concentration of the phytoplankton, or the concentration of chlorophyll and the phytoplankton biomass. But you can see, if you look very carefully, you can see that this pattern remains more or less equal. And finally, the signal in April 15 is not seen anymore. So this is the evolution on a small scale, what is happening in the world ocean, and how this can be seen either from the temperature, but also from the chlorophyll, as you can see here. So that's how we can study the dense water formation, not looking also at the temperature and salinity, but looking also, for example, at the one parameter which is not directly but indirectly related to the vertical mixing and to the biological properties of the ocean. Another thing is that this is very useful way of studying it in the Adriatic, because it's much easier to come here than than be present in Labrador with these huge stores which are there. Anyhow, and with this I would like to finish. I repeat again. If you have questions, please send me the mail, and I will try to reply to you. If I receive the mail, I will reply to you as soon as possible. And that's it. See you on Friday. Okay? Have a good time.
Okay, thanks.
Okay. Everything okay? Did you have problems following this?
No.
Good. Okay. It's too simple?
No, it's okay.
Okay, good. Okay. Thank you very much, and see you around.
Thank you
Thanks
so much.
Bye. Thank you.
Bye.
Bye.
Bye.